Welcome back to our course on the history of mathematics. We are going to continue to Chapter 3 of Hollingdale's Makers of Mathematics, which discusses Euclid and Apollonius. And I'd like to give a bit of historical orientation here. So when we refer to classical Greece, we are talking about the period of roughly 600 BC to 300 BC, where the center of cultural activity was in Athens. And just to give you some orientation, Socrates and Plato were active during this period. Now, what separates the classical Greek period from what our author calls the Hellenistic period is Alexander the Great. Now, Alexander the Great conquered a bunch of territory around the Mediterranean Sea, and that leads to a spreading of Greek culture outside the city-states that were active in the classical Greek period. So the Hellenistic period goes from 300 BC to 600 AD, and the center of cultural activity shifts. It's no longer in Athens anymore. It's actually in Alexandria in Egypt or North Africa. And in this city of Alexandria, there are several important features, one of which was the founding of the museum. Now, that is not a museum in the sense that we would use the word today. It's a museum that was actually a university. So it was a center of teaching and also research. So they're looking to pass on the knowledge that they already have and also looking to create new knowledge. And the library at Alexandria was the largest one in the ancient world. So, as the title of the chapter suggests, Euclid is one of our main points of interest, and an important bit of Euclid's legacy is Euclid's Elements. This was actually a collection of 13 quote-unquote books that contain 467 propositions that covered geometry, arithmetic, and number theory. And propositions 47 and 48 in Euclid's Elements cover both the Pythagorean theorem and its converse, which we have already seen. Okay, so Euclid's Elements was a synthesizing of essentially all the known elementary mathematics from the classical Greek period into one cohesive work that built up logically from definitions, postulates, and common notions, and then proceeded to provide proofs, deductive proofs for all the propositions in the work. Okay, so I want to talk about an important feature in Euclid's Elements. This is a proof that every mathematics student should know, and this technique should be familiar to us all. Okay, so the claim is that there are infinitely many prime numbers. So once again, proceed by contradiction and assume that our claim isn't true. We'll assume it's false. So we'll assume there are finitely many prime numbers. Well, in that case, we can make a list that contains all the prime numbers. So this list, P1, P2, P3, and so forth and so on, all the way up to Pn, is our list that supposedly contains all the prime numbers. Now we're going to define a new number, which we'll call Q, and we're going to define that number by taking all the primes, multiplying them together, and then adding 1 to that. Now, I'm sure you remember the fundamental theorem of arithmetic. It says that every number is either a prime or it can be expressed as the product of primes. So everything is either a prime or a composite. So this new number that we've created is either a prime or it's a composite. So let's look at these two cases here. So case 1, well, if Q is a prime, then we've actually created a new prime because Q can't be equal to any of the P's on our list, and that list supposedly contained all the primes. So that list is incomplete. Okay, let's go on and look at case 2 here. This is a little subtle here. If Q isn't a prime, well, we do know that none of the primes on our list can be a factor of Q, because if we take Q and we divide it by one of the P's on the list, we will get a remainder of 1. That plus 1 at the end will be what's left over. So the prime factors of Q cannot be on that list. And in either case, that list that supposedly contained all the primes was incomplete. So what we conclude is that our premise of being able to create a list that contained all the primes was false, because we just provided a procedure that allows us to take any list of primes and create ones that are not on the list. So no matter how big your list is, it will be incomplete. Okay, here's a little thing I would like to do. I'd like to look at a way to use the method in that proof to take a list of primes and generate some new primes. So let me take some primes that I know, 2, 3, and 5. Let's just pretend those are all the primes that we know. So if we follow Euclid's procedure, we would define this number Q to be 2 times 3 times 5, and then we would add 1. Okay, the arithmetic there is pretty easy. We can do it quickly, and we see we get 31. And this is a new prime. So our list that originally contained 2, 3, and 5 can be extended to 2, 3, 5, and 31. Okay, let's suppose we had something a little bit longer, a list that's a little bit longer. Let's go with 2, 3, 5, 7, 11, and 13. Let's say those are the primes that we know. Those are all the primes that we have. So we will form our new number Q by taking the product of everything on our list, 2 times 3 times 5 times 7 times 11 times 13, and then when we have that, we'll add 1. So let me just do some calculations real quick. 2 times 3 is 6, times 5 is 30, times 7 is 210, times 11 is 2,310, times 13 is 30,030, and then if we add 1, we get 30,031. Okay, now I did a little bit of homework on this, and this is in fact not a prime number, but it is equal to 59 times 509. So 30,000 rather, 31 is equal to 59 times 509. So we got a composite here, but it turns out that both of these are prime, as you can check. So these are both new primes. So sometimes doing this procedure generates more than one prime. So starting with this list, we can apply Euclid's procedure and create a new list from our result. So our list of primes now is 2, 3, 5, 7, 11, 13, 59, and 509. And what Euclid's proof assures us is that no matter how long our list is, we could always do this and get primes that aren't on the list. Therefore, no list can contain all the primes. So, very interesting proof and a technique that every student of mathematics should know.